Hello everybody. So let's continue our discussion on signal space representation. So our objective was to represent a signal that is selected to represent a binary word in the signal space diagram, for which we said that we should be in a position to represent the signals as a linear combination of a set of orthonormal basis functions. So we said, having known the set of orthonormal functions, it will be possible to represent or to synthesize the signal of our interest. And similarly, the synthesized signal, if it is transmitted, the receiver will always know what are those orthonormal functions using which it will design, it will implement the correlation receiver, and which we have already seen as an analyzer. It looks something like this. So if you have got Si of t is received, then you can always generate phi 1 of t integral So if we transmit Si of t corresponding to a binary word, and if receive without any noise at the input of the receiver, then we can calculate this vector. This is called a signal vector. This vector will represent the n values, 1, 2, 3, 4 n values corresponding to the ith signal. So it is one signal vector. Let us call this signal vector as Si, for example. Let me call it as Si. One signal vector corresponding to Si of t. That means this Si of t is mapped to S. So Si is mapped, this vector is mapped to this signal. Okay. So we can go and place this vector as a single point in what is known as a signal space. So let us say this is an n-dimensional signal space. Physically we can imagine only 3 dimensions, x, y, z. But in this case, in the signal space representation, let us imagine there exists a space, the n dimensions, which are mutually orthogonal to each other, and the mutually orthogonal signals are phi 1, phi 2, phi n, and along each of these directions there exists an amplitude. So all these things put together will constitute a vector, and this vector can be used to represent in the signal space. So I just take example of a 2-dimensional space in order to understand easily. Phi 1, phi 2. So one of these signal will be placed here as a point. Done. Now, if the signal is received with the error, what we normally receive is x of t equal to some Si of t plus W of t, where W is there. W of t is a band limited white noise. Okay, sample function of the band limited white noise. for which the mean is equal to 0 and the PSD, power spectral density, is equal to n0 by 2 watts per hertz. This is watts per hertz. So this is the noise waveform which is getting added to the transmitted signal, and what we receive is Xi of t in the input of the signal. And because of which, what might happen? Now instead of I of t entering into these correlators, what will enter is x of t. So then what will be the output? Si of I1. What will be Si? Will be Xi1. So Xi1 would be the same thing. X of t integral x of t phi 1 of t phi 1 of t dt. This is the output. Now here this can be written as integral 0 t. X of t can be split into this Si of t phi 1 of t dt plus integral W of t phi 1 of t dt. So this we already know, Si of t phi 1 of t. So is what is it? Si1. That is Si1 plus this we can call it as W I. Okay. Corresponding to at that during that time duration W1 I and 1 in this. Similarly, we can find out the Xij. Okay, Xij to be Sij, Xij to be this one, and Wij. So where J is varying from 1 to. Okay. So this is an n-dimensional vector. Corresponding to a signal S1 of t, you get x1, 1, x1, 2, x1, 3 and that vector. And corresponding to signal S2 of t, you get another vector like that. Or any Si of t, you get different type of vector. So you can go and place this vector. This was only say Sij. This Sij we have placed. Okay. Now we are placing Xij. Xij is equal to Sij plus Wij. Wij is contributed because of the noise. So this noisy Xij, this noise can be plus or minus. So this point can either move in this direction or that direction. Suppose, let us assume that phase angle everything is same. So in this point can move here. For example, it can move here. And if the noise value is different, this may move here. Like that, this one point may either move here, here, or anywhere. Okay, like a cluster. It will be around the cluster. Because of noise, this point will move anywhere in the space. Anywhere in the space, depending upon the amount of noise. We said that a meaningful transmission can take place only when meaningful means errors which are acceptable, 10 power minus 5 or something like that, can be done only if the signal to noise ratio is more than at the input of the receiver, it should be more than 30 dB or 40 dB depending upon the modulation. So signal power will always be more than the noise power. So the deviation from the mean value, this is the mean value around which this change will take place. It may go like this, like that. If this point happens to move from here to here or here, then it means the noise value is much more than the signal power, which is of no practical concern. Therefore, we don't consider. So, if you transmit this point, the received vector may be either moving around this. This is a cluster of points. Now we have to make a decision whether what is the transmitted vector. So for which there are a lot of issues which are to be discussed, which is not the concern of this particular course. So I will reserve it for the next course. So what we are finally trying to say is that the representation of the signal using a set of orthonormal basis functions helps us to design a receiver which is of optimum in nature. This is a correlation receiver which is the optimum receiver, and we can prove it later. So, and we can also represent this signal in the form of a point in the signal space. In other words, we can even say that we have converted the continuous form of signal into a discrete type of entity. Okay, this is continuous signal. X of t is continuous signal entering into the receiver, and we have converted into a discrete entity, which will help us to represent as a discrete point in the space, which will give certain idea, certain revelations about the detection process, which we will be studying later. So that is how representation of signals in the signal space diagram helps in understanding the detection process, optimum detection process. Okay. So, in fact, we can say signal has been vectorized or discretized. Similarly, noise was also a continuous noise. This continuous noise now results here as a discrete value. Okay? So, we received a continuous noise. Through this analysis, we have converted it to a vector, and this is a discrete noise. So, that is how it helps in understanding signal space diagram. So, basically, in digital communication, what we will be interested is that we are given a series of ones and zeros which are representing a particular type of a message, and for transmitting these messages we need to select time domain waveforms. We have the option of selecting through baseband communication or bandpass communication, and if it is a baseband communication, the spectrum of the selected signal will be around 0, and if it is a bandpass communication, the spectrum will be around a particular carrier frequency. So, when selecting these signals, we will depending upon whether we transmit something like this, whether we transmit individual, or we select the waveforms for individual bits, or we select the waveforms for a block of bits, 2 bit block, 3 bit, 4 bit, 5 bit, or any n bit block, depending upon the requirement. We have to imagine the appropriate dimension of the space. If it is say 3 bits together, it will be 8 signals, 8 input signals, but whether these 8 input signals require 8 different orthonormal functions, or only 3 orthonormal functions sufficient, or 2 sufficient, it all depends upon how many such, depends upon the type of signal that we select. Okay, so which is not our concern here. So that is about signal space representation of the signals. Now we will try to understand how do you arrive at these particular orthonormal basis functions. So there are many people who have given different sets of orthonormal functions in order to represent any arbitrary waveform like this. Fourier transform, Fourier series is one such example. But let us see a general process which is known as a Gram-Schmidt orthogonalization process, which will help us to derive these functions from the set of signals that we assume.